Hello everyone. Today I'm gonna tell you about my report. Before we start, let me introduce myself. My name is Benay Israel Tualangi. My student number is 2023-32044, and I'm from Class A Information System student. Okay, let's jump into my work. So let's begin by importing the necessary libraries, NumPys for numerical operation, matplotlib for plotting, and Keras from TensorFlow for building our models. First, we generate a synthetic dataset for linear regression, following by the formula y equal 3x plus 2 plus noise. We set a random seed to ensure reproducibility. The scatter plot below visual this data, a clear positive linear relationship, but with a realistic random scatter. Here we have the output. The red here. Next, we define our first model linreg. Using the Keras sequential API, it's the simple possible neural network. A single dense layer with one output neuron. Crucially, this single neuron model is mathematically equivalent to a classic linear regression model. Next, we have here, we compile the model specifying the training parameter. We use the stochastic gradient descendant or SDG optimizer and MSE or mean square error as the loss function, which is the standard for regression tests. The model summary confirm we only have two trainable parameters, the weight and the bias. Okay. Next is the model. The model here are now trained for 100 epoch on our synthetic data. During training, the model interactively adjusts the weight and bias to minimize the MSE. As you can see from the output here, the loss drop quickly, indicating successful learning. Okay. Finally, we extract the learned parameter. The model found the weight to be 2.99 and the bias to be 2.29. These values are remarkably close to the true stating value of 3 and 2. The visualization confirmed the result. The red regression line accurately captured the trend of the original blue data point, demonstrating the NN ability to solve a linear regression problem. So that we have LNN classification, linear classification experiment. Here we shift to a classification task using a new nonlinear data cell called McMoon. This data visualized here consists of two intertwined transient shapes. We split this data into training and testing set. Because the data is curved, it cannot be perfectly separated by a single straight line, which will be key to our finding. Here's the output that comes. Thread, we have model in CLS. We define a second model for classification. Similar to the first, it has single dense layer with one neuron, but we use a sigmoid activation function. The sigmoid squash the output between 0 and 1, making it suitable for binary or two-class classification. And here we compile the the classification model, the optimizer is, and the last function is binary cross entropy, which is the standard loss metric for two-class probability model. The summary show the model has three trainable parameters to wait for the two input feature plus one bias. That here we train the linear classification model for 100 input and make moon training data. So that we evaluate the model performance on the test data. The output here show a very poor test accuracy of only 12%, 12.00%. This confirm that a simple linear model, which essentially draw a single straight line, is incapable of solving a nonlinear problem. We're going to skip this part. Then here we have depth decision boundary. This visualization confirms the limitation. The plot decision boundary function show the model trying to separate the two moon shapes using a single straight line. The defining characteristic of a linear model, because the data is non-linear, the linear boundary fail, resulting in the low accuracy. This experiment demonstrates why more complex network using nonlinear activation function and hidden layer are necessary for modern machine learning. That's all from me. Thank you for watching. Goodbye.